Okay, you follow me? Huh? So the assertion of the special theory of relativity now, which is our topic today, is that light travels at 300 million meters per second. And it's kind of constant. No? So if light is constant and it's traveling through space, then just imagine how fast or how close or near are celestial bodies. No? So celestial bodies, the space, if space divided by time is constant, guys, imagine that. If space, let's say it's traveled by a certain period of time by light, and light is kind of constant, then probably space and time will also behave weirdly, because there are far galaxies and then there are nearer galaxies, and so on and so forth. So space and time. So part of the theory there will discuss about time dilation, and we'll discuss about length contraction. So again, the theory of special relativity. Now we are going back now just a bit, and let's see another video related to this one. And again, this video is still on special relativity. So let's see the second one. So it's kind of loading. Sorry.
Reflect your most up-to-date plans and schedules.
Let's skip that.
Around 1900, all of physics, and particularly Einstein, was in trouble. They couldn't figure out how anything could move. Now, before you complain that I'm exaggerating, check out this cat. You can clearly see that the cat is moving away from Einstein at a constant velocity. But do a little sliding switcheroo, and suddenly it looks like Einstein's the one moving. This is the old-fashioned principle of relativity. But the point is that the switcheroo changes relative things like position and velocity, and not absolute ones like the separation of Einstein from his cat. Now for the problem. Before Einstein was even born, physicists showed that the speed of light was one of those absolute things which can't be changed by a switcheroo. So any switcheroo we do has to keep light moving at the same speed. But then it's obvious that we can't do our sliding switcheroo at all, which means we can't explain how anything other than light can move. Okay, I spoke too soon. There is one solution. Do you see it? We were assuming that our switcheroo had to keep every slice of time at the same, time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too. Of course, Einstein didn't figure out this special principle of relativity in 1905. It was already done by a guy named Lorentz 10 years earlier. But Lorentz just thought that this time rotation was a mathematical trick, and it took Einstein to step in and, you guessed it, propose that time rotation is real, that time really is relative, and that consequently, simultaneous events relative to one observer aren't simultaneous relative to another. Now that's a real switcheroo of perspective.
Okay, so that's our special theory of relativity. So one assumption was that light is kind of constant. It's traveling at 300 million meters per second. And then the other contention is that there's this thing. If it's constant, then there must be something that we have to see at time and on distances, or spaces. Spaces, therefore, could probably be bended, or warp. So again, the idea of length contraction and time dilation. Now our notion of lengths actually is very limited. So since we are on a macroscopic scale, like at our level as human beings, we understand things that are that have dimensions like chairs, tables. And that is on our dimension or on our level. However, you will see that our notion of spaces, guys, may be limited because there are particles that are in the subatomic level, atomic level, like protons, cells. These are still distances, but they are quite small. So again, if we limit our idea of distances on our own perspective, then we would see only a meter, no? But what about those tiny dimensions like in a nanometer, no? Which are very, very short distances already, no? But they are still inhabited by, no, small beings, no? Living things, no? Like cells, no? Like things that are inside a cell, no? And another dimensions would be, you know, something like the size, the weight of a planet, no? Imagine the weight of a planet. How big is the weight of a planet, no? That could probably reach, no, in several thousands, no, or even millions, no? Like, what about the weight of the sun, no? How heavy is the sun, no? Or distances, no, of galaxies, no? So again, no, if we limit our ideas of lengths, then we can only, no, relate to it, no, on our own day-to-day activity. However, no, there are other minute distances and there are other very, very huge distances that are found in space, no? So in several dimensions, no, there are actually, no, varied levels of lengths, no? Okay, so we will try to relate that, no, to our idea of relativity, no? So the dependence of various physical phenomena on relative motions of the observer and the observed objects, no, especially regarding nature and the behavior of light, space, time, and gravity, no, is called relativity, no? When we have two things, no, and if we want to find out, no, the relation between their physical property, like in terms of their velocity, no, then we need relations between them, no, that which is higher and which is lower, no. In general, no, we can in general, no, we refer to it as relativity. The famous scientist Albert Einstein, no, was firstly found, no, out, no, the theory of relativity, no. So what is this theory of relativity, no? So Einstein determined that the laws of physics are the same, no, for all non-accelerating observers, no, and that the speed of light in a vacuum was independent, no, of the motion of all observers, no. So whether observers are running towards the sun or running away from the sun, or whether they are steady, the speed of the light that reach them, no, covers, no, or reaches them at the same rate, no. Usually, no, when you run towards an object, you will increase your speed relative to the object because you are going towards the object, no? So the object will hit you, no, faster if you go towards it, no? Or if you run away from it, no, you'll notice that the object will reach you, no, a little bit, no, longer because, no, again, no, the speed there would be a little bit lower relative to you running away from that object, no? But not with the case of light, no? Light will reach the individual, no, no, at the same speed, no? So regardless whether they run away or move away from it, no? Okay, then there's these equations on the Galilean transformation, no? So let's just look at the first postulate, no? A person playing pool, no, on a smooth and fast-moving ship, no, does not have to compensate for the ship's speed, no? The laws of physics, no, are the same whether the ship is moving uniformly or at rest, no? So once the ship attains, no, a uniform speed, no, so you don't have to play the game of pool there, no, as though you will try to consider the speed of the boat, no, as long as the boat is already moving, no, with uniform speed, no, just like inside the plane, no, when they serve the meal, the drinks, the refreshments, no, they do it when the plane is already traveling, no, at a uniform motion. No, during that time, you don't feel anything. No, your water or your glass does not spill towards you because, again, no, you don't have to adjust, no, your hand, no, holding the cup, no, filled with juice or drinks, no, relative to the plane, no, because again, no, the plane is merely traveling at a uniform speed. Now that same feeling, no, is true, no, when you do the drinking of the cup when the plane is still, no, on the, no, on the tarmac, no, or ara pa siya sa parking areas ng airport, no. So again, no, uh, this is the first postulate, no. So we will not have to consider, no, the moving object, no, when it is merely traveling at a uniform velocity. So you will not really know which one is actually moving. Next, the first postulate, Einstein's first postulate of relativity, assures our inability to detect, a state of uniform motion. Many experiments can detect accelerated motion, but none, according to Einstein, can detect the state of uniform motion. So again, so that's the case. So you will not, the player there of the pool game will not notice anything, even though the boat is actually moving. Now let's go to the second postulate. The second postulate of special relativity states that the speed of light in empty space will always have the same value, regardless of the motion of the source or the motion of the observer. So whether you're coming towards the light or running away from it, the speed of that light is always constant. That's postulate number 2. Now, this ether, the ether is, I believe, that's what they think, that is feeling the vacuum in space, So the our outside the Earth, we know that it's vacuum, so there's no air, so we say that it's a vacuum because there's no air there, but they have this notion that it is not filled completely empty, but they thought of a word ether to have occupied that. So waves require a medium through which to propagate the light. So one thing about light is considered as a wave, and waves needs a medium for it to travel. And they thought of the light coming from the sun to travel through this ether. This is the medium wherein light of the sun reaches the earth, because there is in between an ether there. But actually, this one is proven something like not true, because they realized that light is an electromagnetic wave, and it does not need actually a medium to propagate itself. Okay, so again, this is their notion that fills the empty space, and they term it as an ether. Okay, the Michelson-Morley experiment. Experiment designed to measure small changes in the speed of light was performed by Albert Michelson and Morley. They used an optical instrument called an interferometer that Michelson invented. The device was able to detect the presence of the ether. Outcome of the experiment was negative, thus contradicting the ether hypothesis. So they were able to discover itong hypothesize of the presence ng ether is not actually there. So this one involves a lot of beams of light and some mirrors and some prisms, and that's how they produce the images there through reflections and those principles of the behavior of light. Now the Lorentz transformation, the relations between the primed and unprimed space time coordinates are Lorentz transformations. Each coordinate in one frame is a linear function of all the coordinates in the other frame. So again, so C. Lorentz was again the one who tried to explain the work of Albert Einstein, maybe because of his equation, so on the special relativity. Now, one thing we realize here is that they come up with this equation, guys, that talks about so if you'll multiply together time and speed, we'll get a certain value called distance. Then again, this allows the transformation of this equation, and eventually they come up with an equation for how light behaves. Since light is kind of constant. Now, one of the things that we have to consider when light is constant is this thing called time dilation. No? So if light travels very fast, it can reach the farthest no distance, or maybe the shortest distance no in less amount of time. No? So you'll notice that if a guy no travels fast, no, in his perspective, it seems nga the time there has been stretched, no, because he can do so many things, no, like if you watch movies about what no, a guy that travels very fast, I think he's Flash, no, you'll notice that he can do so many things, no, in just a fraction of a time, no. So although that's a science fiction movie, no, but probably we can think of time dilation in that way, no? So if one travels very fast, then in that very short period of time he can do so many things, no, when in fact no, for us it's just a maybe no the wink of an eye, no. So that happens very fast, but for him no, he can do so many things there already, no. So he dilated the time, no. So we explored the rate of time no, in different inertial frames no, by considering a special kind of clock, no, a light clock, no, which is just one arm of an interferometer. No. Consider a light pulse bouncing no, vertically between two mirrors. We analyze the time it takes for the light pulse no, to complete a round trip, no, both in the rest frame no, of the clock no, labeled S no, and in the inertial frame where the clock is observed no, to have moved no, horizontally at the velocity no, v, no, labeled again S. No? So again, no, what happens is that no, they end up no, with how time is determined no, in relation to the speed of the object and the speed of the time. No? So this is now our time dilation equation. No? The proper time no, in the frame of reference moving now with the clock. No? Now, with time, no, maybe elongating, and we have a constant value for the speed of light, then probably length will also shorten. No? So if you are going to travel no, to distant places and you can reach it no, at the same speed no, every time, no? You can always reach it at the same speed, then probably no, you can either change the time or you can change the length no, in that case. No? So in some science fiction movies, no, you see warp no spaces, no. So they kind of put together two points in space, no, and then they can put it side by side, no, and you can travel through it, no, at equal time intervals, no. And then again, no, granting that you can travel at equal speeds, then probably no that distance could have been changed, no. Again, no, our notions of lengths and distances, no, is always limited at our own dimension or level, no, because human beings, no, we only deal with a meter, a kilometer. But what if again, no, the dimension is so small like that in the case of a cell, no? Again, no, you'll notice that things still not travel on those small spaces. No? So there are still no events and things that are occurring on those small, tiny level. No? And even in the huge no, galaxies that we see no, whenever it's nighttime. No? So length contraction is a phenomenon no, of a decrease in length no, of an object no, as measured by an observer who is traveling at a non-zero velocity relative to the object. This contraction, no, more formally called as Lorentz contraction or Lorentz no, Fitzgerald contraction, is usually no, only noticeable at a substantial fraction no, of the speed of light. No. The length contraction is only no, in the direction parallel to the direction in which the observed body is traveling. No? So again, no, the case of uh, length contraction. So again, no, Lorentz was the guy who tried to explain no, the work of Isaac Newton. And again, one of the contentions of the special theory of relativity is that light no, is a constant value. And again, if one object no, is moving no, in a uniform motion, then you cannot notice that it is actually moving relative to an observer. No? So those two postulates. And again, no, I think no, we will just try to understand that at that level. No? Okay, so the theory of special relativity. Now, with the idea that light is traveling at 300 million meters per second, let's look at the nature of our expanding galaxy. So our galaxy is believed to be getting larger and larger. And probably let's look at some reason why why they claim that not to be the case. Isn't it that our galaxy is getting towards each other? So which one is the case? Which one is really occurring? Uh, there's one theory in physics also, the law of entropy, that everything is going towards random. So if everything is going towards random, some believe that we are disintegrating. We if we will hold things together, usually it involves a lot of effort. But if everything is going towards equilibrium, then probably everything is ending in disintegration. So we can attain eventually the notion of equilibrium. So we can probably link that with this notion of the expanding universe. So if things are expanding, then maybe that's the state wherein we would probably reach equilibrium state. So our galaxies really going further away from each other. So let's look at some reasons why they say that it's the case. So this is our last topic. So cosmology, the study of the universe, structure, origin, evolution, destiny. I think one of the main reasons why we believe the existence of galaxies is this Big Bang theory. At some point, things are very close to each other. They are kind of compact, and then all of a sudden, there's this sudden explosion. Now, I think even before it exploded, so we could have one small object, and sometimes they call it as a singularity, that probably is so heavy, so massive, even though it's so small, and suddenly it exploded and it created the universe. So that's those are some theories. So why do we consider them theories? Because nobody was able to observe them. Nobody was able to document them at the time they occurred. I don't know if you will live, if something exploded, and similar to a Big Bang explosion. So again, the cosmology is the study of our universe. And we have some earlier ideas of how the universe behaves, and we've covered that over our lecture. There were those who believe that the Earth has been the center of our universe, of our cosmology. All things goes around the Earth. So the Ptolemaic theory, or the Ptolemaic notion of the center of the universe. Now comes Nicholas Copernicus, who said that the sun is the one which is the center of the universe or cosmology, which is not true also. So again, things like this. So is the sun really the center of the universe? No. We know that at some point the sun is where our solar system goes around, but the sun is not literally the center of the cosmos. So again, something is improving, but at some point, some of these notions are also not right. And on the 20th century, we have the Hubble telescope. The one who made it is Edwin Hubble, that now postulated that the universe is also changing. He's the one who says the universe is expanding. And how did he come to that conclusion, or how did he come to that idea? So we will try to find that out. Now, the expanding universe, the Earth being the center of our cosmology, of course, created a lot of problems. So the stars here are fixed in what they believe to be a celestial sphere. So it's like a hollow ring around the the cosmos, and that's where the stars are fixed, no? So which is not true, no? We discovered that they are not true, no? So the Earth-centered model predictions, no, future planetary positions. That's where it really, no, conflicts itself, no, because it's very difficult to predict, no, because they're, aside from they go around the Earth, no, these planets also go roundabout, no, in its orbit in a circular manner, which they call as epicycles, no, or the retrograde, no, motion, no, which conflicts, no, or complicates the computation. But however, now people believed it for 1500 years, no? So that's how long it was believed on until, no, they, no, they were able to create, no, some challenges to it, no. Now one of the problems of that model was, again, no, the unpredictability probably of the phases the of the planet Venus, no. So if Venus appears like the moon, no, which comes in varied phases, so there's a problem in how it appears, no. So again, no, after that theory comes the sun-centered cosmology, no, where everything goes around the sun, no, which was uh, which Nicholas Copernicus came out, no. At rest, however, no, in the middle of everything is the sun. No? And if that's the claim, then the sun is not actually the center of our universe, no? As we will realize today. No? So the sun-centered theory, no, future planet positions, no. So it cannot also predict it, no, because Kepler was able to realize, no, or to give us, no, that the motion of the planets are in, no, elliptical orbit, no. So now the sun-centered model also, no, could not determine the movements of the stars, guys, no. At some point, the stars kind of travel, no. Why do they move? Probably, you know, that's where the problem with the sun-centered model, no, was not able to explain. No? So again, no, although it may be relatively correct that we go around the sun, no, but the sun is not fixed, no, and just like the stars, no, because stars at some point observed from two locations on the Earth, no, will have, no, no, a varying, no, length, no. Now the Big Bang Cosmology, no, Albert Einstein, no. So if there's that thing really, you know, about a huge explosion that happened a long time ago, no, then there must be traces of it still existing, no, like a smoke. You know? And I believe, no, they were able to realize that, no, or observe that, no, with their careful observation of space, no. So again, no, giving them the notion or proof that Big Bang really happened, no? Because if there's an explosion and space is it does not dissipate, no, it does not have an atmosphere like the Earth, then that smoke must still be in existence, no. The universe now is expanding, no? That's the prediction of the Big Bang model, no? So it started with a small thing, then and it exploded, no, then that motion probably is still going on today, no? It is still ongoing, no? So they started the belief, no, sometime in 1929, no? And probably this is the time when they, no, when they discovered that telescope, that huge telescope they call as the Hubble telescope, no?